So it's my pleasure to introduce Deniz from PCM, which will talk about the particular algorithm for maximum marginal likelihood estimations.
Yes, thanks Alan. Thanks Alan and Eric for the invitation. It's great to be here. Also, this is joint work with Francesca, who is, some people know here, Tim, with PhD student also Piers, Mark Girolami was joined at Cambridge at Turing, and then Sotiris, well, he's at Edinburgh and also a professor in Athens. So this is a talk about basically the workshop is about generative models and for inverse problems, I think. So this does not have generative modeling, except that this can be applied to generative modeling, and then this does not have any inverse problems except that it can be applied to solving inverse problems as well. And the generative modeling bit is the background picture generated by Darling, right? So it's okay. So I'll do this. Should work. I suppose we can. Let's see. Yeah. So because the background varies in the room, as far as I was able to observe, so that half of the talk will be mainly like reviewing what I call diffusion-based MMLE methods, so maximum marginal likelihood estimation methods. So I'll review a few existing approaches, and then this paper we wrote that's on archival preprint now is a book fast evolving as well. Is basically the idea was to analyze an existing algorithm, one of these algorithms that I introduced, but slightly modifying it because the analysis required a slight modification. So I'm going to introduce the algorithm after the review, and then I'm going to conclude and mention the future directions, which I think there's many of them. Okay, so we consider a very general setup here. So the setup is basically a bit like yesterday, what Marcelo explained. So we have a joint probabilistic model, right? So this is what I call a probabilistic model. There's a parameter theta. Well, let's start from x. X denotes the latent variables, right? These are the things that we will not observe. So this is just the x dimensional sort of, the space is always RD, RDX, RD theta, whatever. So nothing fancy. We have a parameter that's called theta. And we have data, right? So one of the things, so y is here data. And one of the things that's going to be fixed throughout the talk is the data, right? So I will never consider y as a random variable, rather than it's going to be just small case y, that's going to be fixed number. So it's because we will compute posterior distribution conditioned on theta, and we are going to try to estimate theta, right? So y is fixed throughout the talk. So we are basically interested in two main quantities in this kind of setting, right? So you would want to estimate, so given a generic probabilistic model like this, so I don't even specify how this factorizes, right? It could be factorized in different ways. What I mean is parameter could be in the likelihood or the prior or the both, right? So theta would be our interest, the optimal parameter. Of course, theta star, when I say theta star, the question is whether it's unique, whether there is a single parameter that could be called optimal. That's of course, depending on our assumptions I will make. And of course, in this setting, also given theta star, you would want to sample from the posterior distribution of latent variables, right? These are the two things that you would want to typically sort of obtain in this kind of setting. Okay, so this problem covers, of course, as you can imagine, many statistical machine learning settings based in statistics problems, as we have seen a bit like yesterday, Marcelo's talk as well. So there's a lot of applications. So I'm just going to have a slide of what applications could be. Machine learning problems, like things like unsupervised learning problems, because unsupervised learning, you always can see the latent variable as the features and the theta as the parameters that is in the embedding parameter, for example. So probabilistic matrix factorization is an example. Statistical inference problems, which overlaps with this, of course, and parameter estimation in model, probabilistic models, deep latent variable models nowadays, they're called. Inverse problems, depending on what setting you sort of formulate. For example, one setting that's possible is if you use what we call a statistical finite elements formulation, which gives you a conditional distribution of your PD solution given the parameter. And of course, if then you observe the field where I now call it X, then you have this sort of, again, observation latent variable and the parameter setting, right? Parameter will be here the parameter of the forward map of the PD, for example, or SPD in this setting, I think. And generative modeling. So I will not go into this, but this sort of algorithm I will introduce is like exactly very similar to what's called out there in like contrastive divergence, right? So it's the algorithm is very similar. So that's the relation to generative modeling. So this sort of problem also this you have latent variable data and theta can be also found in generative modeling. Okay, so what we are trying to do, so we have a joint probabilistic model, and we define the marginal likelihood, right? Again, y is a fixed data, so y is not a variable. So this confuses a lot of the mathematicians I collaborate with. They say it's pure y, so it's a function of y. Actually, it's a function of theta, right? So we have a joint distribution that y is fixed. We integrated x out. So this quantity is like a normalizing constant in the base rule, right? And it's just a function of theta. So we want to maximize this quantity in order to find the parameter of interest that fits best the data, given that all the latent variables, so all the possible latent variables are marginalized out, right? Just summed over, basically. So this is the problem we want to solve. So we have a probabilistic model. We define marginal likelihood as an integral of this joint distribution, and then we want to solve this argmax problem that we want to find theta star. Of course, it's a different than just standard, MLE problem, because in the MLE problem you are given this. So you are given explicit distribution. You just solve an optimization problem and get your MLE solution. Here it's a bit different because we have a loss that is an integral, right? So log of an integral in particular here, right? So it's a bit of a different problem. So you have to handle integration first, then you have to maximize these things. And of course, the assumption will be here, we cannot just IID sample P or X is here. So we don't have an unbiased estimate of the gradient as well. I'll mention this in a bit. Okay, so then, of course, when we get theta star, we can also solve the posterior inference problem with your favorite sampler. You can run a Langevin algorithm on this or other things that you can do. Right. Okay, so the classical approach, which I will not, again, talk too much about, but I'll just describe because the algorithms I will describe are motivated by the EM sort of view. And also, I'm glad that Eric is not here, he's the expert on EM, so if I say something wrong, he's not going to catch it. So the algorithm for one step proceeds like this. So EM is the typical approach to solve like this optimization in latent variable models problem, right? So the algorithm, of course, why this algorithm is in this form is a separate discussion. But just to describe the algorithm, it proceeds given a theta t, right? Let's say you have theta t and you want to update theta t plus 1. So that's like an iterative algorithm that you update from theta t to theta t plus 1. Of course, the hope is that then this is going to converge to theta star in some sense. Whatever that theta star is, I haven't said yet, right? Whether it's unique or not. So what the algorithm does is it computes its expectation, right? So this expectation is here, theta t is evaluated here. So you have a posterior distribution with respect to theta t. Of course, this quantity is intractable in itself, right? So let's say that you find this first, and then you compute this expectation, and this theta is, you can see that this is the free variable. So this is what we're going to maximize. So you maximize this expectation, right? This is what's called, why it's called expectation maximization. So you always compute this expectation first with respect to this posterior, and then you maximize it in one step, and then you iterate this, and then this is the EM algorithm, right? And then there are some guarantees. Obviously, there's a huge literature there. Most of it is also written by Eric, that these things can converge to stationary points. There are under different settings as well. For example, if you can draw IID samples from this, then it's a stochastic optimization problem, right? If you can't, then that's the setting I will consider. Of course, it's expected or hoped in many cases when this is implemented in practice that this theta t converges to some sort of nice parameter theta star, right? This is basically the algorithm there's a huge amount of papers on applications of this algorithm in all sorts of fields. But so far in most of the literature, people actually have been finding analytic sort of cases where they can do these things analytically mostly, right? Of course, then there's also Monte Carlo EM algorithms where some of them assume that you can do this sampling IID in an IID where some of them assume that you can do maximization, and there are a lot of variation. Okay, so this is the algorithm, the EM. So there are two problems here if you look at it in the most general way, right? So first of all, we require a compute an expectation, which is a sampling problem, right? We need to compute first of all samples well. It's not computable in closed form, that's the assumption. So you need samples from this posterior distribution first, right? And then once you get these samples, these are mostly probably approximate samples as well. Then you have to do maximization, which is again probably intractable, right? Then you have to plug it samples here, then take a gradient and do some sort of numerical optimization. That's sort of sort of a way to approach solving this problem. So one thing going forward, I will do this, use this notation now. I'm not sure if it's the best slide to introduce, but I'm going to do it anyway. So in order to sort of simplify this problem and then describe the algorithms I will use, I'm going to denote this quantity, which I am maximizing expected this quantity in some sense. I'm going to denote this maximum, so negative joint likelihood as U of theta. So you can see now, I'm simplifying things in some sense because I kept saying that Y is fixed. And I ignore Y because it's a fixed data set. I call this U is only a function of theta x, right? And next observation is that it's going to help us to sort of simplify the problem and use sort of diffusion-based techniques, is that the marginal likelihood can be written in this form, right? So it can be represented in this form. So it's sort of an observation that I will use later. Okay, so what do? People do these things to solve this problem. So they run an MCMC chain, so they get theta t, right? And they fix theta t and they need samples from this posterior. They run an MCMC chain for the E step, right? So they run it for a while, they get some samples after convergence, well, or after sort of some burn-in steps. And then they run numerical optimization. For example, they take a gradient of the resulting loss, samples plugged in here, and then they sort of take a gradient or two, depending on what you can, right? Okay. All right. So what's the problem with the classical approaches is sort of hard to prove, or at least when I sort of searched the literature, there were very few papers that actually had explicit rates, especially nowadays, Mala or Metropolis Hastings algorithm, they started there are rates out there, so they could be used, but the classical approaches that were published using Metropolis Hastings and so on, they were not explicit convergence rates. Also, I don't know how much this is true anymore, but the story around Metropolis Hastings, people start skipping it, especially Alan with the EULA, is that sometimes Metropolis Hastings based algorithms can be inefficient in high dimensions. So for these two things is going to motivate what I'm going to describe next, right? We are going to try to do some sampling of this posterior without using Metropolis algorithms as well, and try to get a sort of rates. Right, so this, of course, resulted in using unadjusted Langevin-based methods for this sort of problem. So I skipped a whole bunch of literature now. I'm just going directly into what people did.
I mean, you only the minimization step, maximization step is not sampling, right?
No, that's optimization.
So isn't that a bit like stochastic plane descent?
Yes, but you don't have IID samples, right? Yes, it's a bit like that, but it's not exactly, because if you had IID samples for posterior, yes.
Right.
But if you don't have, then the gradient is biased, and there's also all sorts of problems there. So let's say I have approximate samples from this.
Then you have. I mean, these are
Yes.
marginal.
Sure, but in theory, I mean, it's never there, right? Yes. So if you run the chain long enough, then it's almost stochastic gradient descent, you can say.
Otherwise, you potentially have to die.
Yes. So that's actually what Alan and Marcelo wrote a paper about. So I'm going to mention it in a bit. And that's exactly. So before that, I don't know if everybody's, but most of the people I know that they are familiar with Langevin diffusion, but I'm going to just give like a few slides of this Langevin STs and EULA algorithm in general, so that everybody follows what I'm going to do next. So I'm just going to mention what is this unadjusted Langevin algorithm and the Langevin STs are all about. So this part of the talk, of course, separate from sort of the other parts. This is just the notation in itself, right? So this is a generic drift. So you might have heard about this Langevin ST. So this Langevin ST basically is an ST that looks like this. So you have a gradient, so you have a drift gradient of some function, right? Minus, depending on how you like to write it. And it's driven by a Brownian motion, right? And why it's so appealing for sampling is that, of course, when you're given this sort of distribution, we know that the stationary measure of this distribution has this form, right? So if you put here your grad log density, or log density instead of V, you can easily use this for sampling. Of course, this is in continuous time. Before discretization, you can't in practice, but this tells you why this is so appealing, right? And also another nice result about these things is that this convergence rate of this sort of diffusion to its stationary measure is, if the potential is strongly convex, it's exponentially fast, right? It's the exponent in the exponential is driven by mu, basically. Okay, so that's appealing. And there's another sort of related thing I will use, related result. There's another version of this Langevin ST you could call with if you put basically scale the noise with parameter that's usually in statistical physics called the inverse temperature parameter. There is a slight modification of the target measure, right? This sort of thing results in this sort of target measure. This is what I'm going to use this result, so that's why I have a slide on this. And this is also appealing because we know that if beta grows, so for large beta, this distribution tends to concentrate on the minima of V, right? So here you can see on the connection between optimization and sampling here. So what this means is if you run this thing with a large beta, right? This is true, by the way, for very, very weak conditions. So non-convex VE and you can actually get explicit rate in terms of beta, even in the non-convex case, if your potential is dissipative, for example. So this is a very general result. So this is appealing for optimization, global optimization. A lot of people use this for global optimization because for large beta, then this thing is going to concentrate on the minima of V, and if you run the sampler, then you're going to populate the minima of V mostly, right? With large probability, you can say. So Langevin diffusion can be seen as a global optimizer, right? This is one of the reasons why it's popular in optimization. And of course, then there is this discretizations of yes.
Sorry, why does it really into the moon?
Well, I mean, if you see that the large number of this is going to make the sort of, because you are exponentiating and then this beta sort of amplifies this function.
Just because of the
yeah, exponentially. You can see that.
Temperature is zero. Beta is inverse temperature.
Yeah. This is true. This is sort of remarkable. Also, it's important to what I'll introduce next because this is true also for the non-convex sort of V. This is going to be sort of useful for the extensions of the algorithm I will describe as well. We did only in the convex case, obviously, but in the non-convex case, of course, yeah.
So just the intuition is how this works. There's just kind of like some of the sample we use with a marketing color where you have kind of temperatures, the coupling arguments. So you're saying as the beta goes to infinity, so basically the variance, this becomes deterministic. The closer it becomes deterministic, the steeper the V function is. Essentially, it's easier for the margin.
Well, it's actually, I don't think it's that simple. For very large beta, you have another problem because the thing becomes very steep on maximizers, but like very flat on the other regions as well. So it's not that easy. It's actually in theory it has to be like that, but also it also causes other regions to be flat. So it's not that easy for large beta to direct. But that's why people do annealing. Because if you do, because if you just set it very large, that's what theory suggests. Set it very large and forget about it. So because then you're going to eventually converge to global optimum.
But you're getting some of the local maximum and on the
Yes, but then what in practice, if you implement it, very large beta causes very flat regions as well, which is hard to navigate. So that's best to do annealing in practice. But that's also like the sort of the diffusion models using this annealing idea as well. Otherwise, things don't work. Really. So there is this then. So how can you use this diffusion? So we said that there is an appealing theoretical property, right, that converges exponentially and so on. So how can you discretize this with an Euler discretization scheme? And that's what's called EULA, right? An adjusted Langevin algorithm. And of course, Alan and Eric have written this sort of very nice paper that has led to a lot of activity in this field that you can prove very nice explicit bounds for EULA for its bias and convergence rate in terms of like dimension of the state space. This is mu in my notation, so from convexity constant. This kappa depends on the mu and Lipschitz constant. There are a lot of assumptions, but you can basically say one term there is here that is going to decay exponentially fast. Of course, this is sort of some sort of exponential convergence, and then you have a bias that's non-vanishing because of the discretization error, right? So the order of step size here for the Wasserstein square. This can be improved under various settings and so on, right? This is why it's so how it looks if you implement just a simple order discretization. Here is the price you pay with the bias, right?
All right, actually, a couple of questions. So what is unadjusted?
So normally you have metropolis adjusted Langevin algorithm.
Okay, good.
But you skip it here, obviously. So you just run some sort of gradient descent plus noise, right? And there's no adjustment.
Okay.
And then skipping that causes a bias, which we observe precisely here. This never goes away in iteration, right?
And what is the meaning of W?
So W is in, because after discretization, this is basically a standard IID random area, right? I mean, if you know the Brownian motion, this is an increment of the Brownian motion from the, right? And then this comes from the fact that your gamma sort of time step taken.
Right, so instead of a Brownian motion, you have.
Yes, because Brownian motion is a continuous time process. When you discretize and implement something that you need. So this is coming from precisely of the increment of the Brownian motion, obviously, but this is also implementable, right? You can just go and sample IID caption variable and then implement it.
Another thing is, I don't know if this is important talk. I don't actually understand what's going on in the equation.
So here, yeah, this is, thank you for this. I think I didn't explain. So this is the Wasserstein 2 distance, which I am not introducing because not very relevant for the particular formulation, but this is the distance between probability measures, right? And it's good for me to slow down here. So what this says is that, okay, I'm given the teeth iterate of this algorithm. So this is the teeth iterate, let's say this one. And this is the distribution of that iterate, right? The law of the iterate. Distance of this is to P star, which is the stationary measure that I wanted to sample from, that motivated. So this is the grad log of P star, right? Again, another thing I didn't say. So this is the distance to the target measure, right? And it's upper bounded if you use this algorithm by this sort of term here. So you have a sort of this term, you can see decay. So this is less than 1. That's why I'm saying under suitable conditions. This is going to decay as T increases, right? And the dimension dependence is very explicit here as well. So this is the D, the dimension of X, and M is the strong convexity constant, mu. So also another thing I assume here that D is strongly convex, mu is strongly convex. And then this is the distance to initial condition, right? So this is going to die with this T increasing. And this gamma is the discretization step size, which incurs a bias because I'm discretizing a continuous time system. And because I'm not doing metropolis hastings, this Wasserstein 2 distance is never going to be sort of dying because there's going to be always bias, right?
Sorry, what is X star again?
X star is the optimum. So because I assumed V is strongly convex, that's the maximizer or minimizer of V.
And K or kappa is Imperial.
So kappa is there's some expression too. So that depends on the Lipschitz constant of V and the strong convexity constant. But I didn't explicitly write it here because this is sort of a review of the literature. But this is 2 ml divided by n plus L of something. Okay. All right. If you have.
Just to order that, sorry.
Yes,
we get beyond the slide there.
Yeah.
I mean, if you replace P star by P star gamma, then all that changes that gamma disappears in the estimate.
Yes.
Right?
Yes.
And if you do
yes, I think maybe I was just.
and if you do Mahler, what is changing? The gamma again disappears and
So
constants are changing.
I cannot say actually that because it's not easy to get this sort of bound for Mahler, I think.
Okay, not available.
Well, I mean, I think very recently they are, but I didn't read them. So it's not as easy as, okay, if you're Mahler, you just drop this term.
Yeah.
So it's a completely different sort of analysis as well. So I'm not sure, probably Alan knows it. Yeah, so.
What is the small X?
Which one? This one?
Yeah.
Initial point, yes. It has to be x0 or something. Yes. So this is driven by the initial point, distance to the maximum. So how far you're away from the maximum squared, and then these terms, and then other stuff. Yes, I'm going now. Going behind. Okay, so EULA, of course, as any MCMC algorithm can be used for Bayesian inference, right? And just for again simplicity, I'm giving it here. So if you want to sample from this sort of posterior, of course, the posterior is proportional to this sort of joint distribution. So this could be likelihood times prior. And if you just compute the grad log of this guy, so there's an unnormalized density, but you don't need normalizing constants because they drop out. You can use this sort of algorithm for sampling now from the posterior approximately, right? Yes, I think this sentence I forgot to correct. This is wrong. So would not have the stationary measure. So if you run this would not have the stationary measure posterior, but this would approximately sample from posterior. So and then just to remind you the notation I was using, remember I was saying that I'm going to use log P of xy as I'm going to denote this as u x theta because I don't care about y anymore. So equivalently, this thing can be written like this for fixed theta, right? So if I run this for fixed theta, so this is now P of theta x comma y, or the log of that, then this would approximately sample from, it wouldn't have a stationary measure, but it would have something close to this. as U is this, right? Okay, so this is going to be sort of useful for me.
Sorry. So the EULA is the unadjusted.
Yeah.
You're not using asymptotic.
No,
So you don't ever have that kind of factor which asymptotic gives you. So you start finding your a local maximum when that's I guess in this case a local minimum.
yes.
The asymptotic always gets you back out, right? That's the basic idea is you have to claim for some type of adjustment.
Yeah.
Is this how this guarantees your reusability?
Well, this does not guarantee irreversibility, but the noise eventually gets you out of local minimum. But also, I shouldn't go into that discussion because I'm always going to consider you for the potential strongly convex.
And why are people using this as opposed to just doing the claim but the establishment compensation expensive?
So in some cases, yes. Also, the problem is, let's say you have a lot of data points. So Y is sort of millions of data points, where the likelihood, so you can get easily a stochastic gradient and do this sort of thing, which people have also derived guarantees for. For the metropolis, in order to do it exactly, like correctly, you have to evaluate all your likelihood. And that could be very expensive. And if you do a cheap approximation, then you lose the, like, is it correct? I think there is some noisy metropolis Hastings papers, but one of the reasons is this ratio could be expensive. But the attractive part of EULA, of course, then you can replace this with a stochastic gradient that's called SGLD, stochastic gradient Langevin dynamics, where you can again prove some similar results to EULA in terms of convergence, but the gradients are really cheap. So it's scalable. Okay. All right. So of course, EULA has become very popular in the literature. People have used it for many things, and also people use it for this sort of maximum marginal likelihood estimation. It's Valentin's paper with Alan and Marcelo. So people have used, of course, this for now what I described as the EM. So remember in the EM, so I was trying to implement the sampling step, or what I call the MCMC step. Now you can implement it with EULA, right? Let's say you run some EULA chain for some time, you get some samples, and you can use it to estimate your gradient. You do some sort of gradient, sort of descent, ascent, and you know, that's basically how the algorithm goes here, right? So the algorithm basically reads as something like this. You have you can consider sort of the final value of the previous time chain here, right? You can start your chain at time t. So this is called the warm start. You can start your chain at time t from this sort of previous test point. So what you do is for the MCMC step, you run a EULA chain for some time for fixed theta, right? You get some samples. And then you use these samples, you can use k of them. So discarding some initial samples maybe, to estimate this gradient, right? Once you estimate the gradient, you do gradient descent here, right? So, but because I'm using U instead of ascent, or it's always descent now, so because minus U is the, so U is the minus log of the jump, right? Okay, so you can use only last k samples, and you can do gradient descent. So this is the algorithm. And of course, there is a lot of nice analysis in this paper. It's also based on one of Eric's papers about proximal or third gradient algorithm. So the problem here, not the problem, it's a good paper, but the sort of the complication here is that the gradients are biased. The reason gradients are biased is, of course, that this chain sort of it never converges, right? It's always sort of going to converge only n goes to infinity. So the gradients are sort of biased. So you have to account in the analysis for this bias. And then the number of EULA steps has to be sort of small for tractability in terms of like you don't want to run an infinite number of MCMC chain because you can see you're interleaving the theta steps with sort of running an MCMC chain. Of course, then you don't want to run this to sort of super long because it's going to be a slow algorithm.
Would you actually have a decaying step size down there?
Yes. So well, I wrote the fixed step size case. Yes, normally, so one of the things that was in the analysis is that either step size was decaying or the batch size was growing. Sort of, which also was I think like this also in the EM literature there is a lot of this increasing batch sizes kind of results, right? Okay.
Sorry, another question.
Yeah.
So bias, is there a systematic bias where every gradient is locally biased?
Every gradient is what?
Locally biased. Sort of.
Local. What's the question?
Well, what I mean is how bad is the bias?
Well, that's the question, right? So because EULA converges sort of in the convex setting, you can say something about how fast it decays the bias, but I don't think it's that easy. But I mean, they did the analysis here, so you can actually ensure with decreasing step sizes the convergence. Sort of you have to look at the paper. I think this is sort of a there's a lot of results there, so I haven't studied. Yeah. Okay, so another approach that is now I'm going to lead to what I will call later IPLA, right? Another approach that is very recently in the literature, of course, this is based on what Radford Neal and Godfather of AI did in '98, and then Juan, who is at the moment I think a postdoc at Warwick, took this idea then and converted it into an algorithm. There was this approach in the literature where don't ask me any questions on this, right? Because I am not an expert on grading flows, but there was this approach in this paper saying that you can see the EM algorithm as sort of a coordinate descent on a functional that is defined on now. Theta is the normal theta as we know, V is a probability, nu is a probability measure, and you can see the EM as like a gradient to coordinate descent on this sort of functional, right? One argument is the probability measure, the other argument is theta. And there was this sort of proof, I think there's both in this paper and this paper, that this minimizes of this loss, theta star and nu star, exactly gives you the theta star you want, and nu star would be the posterior you want, right? Well, this is I think under some strong conditions, but again, this part is not really my expertise. But what I got from this is that Juan basically took this approach and constructed this set of STEs to basically solve this problem. And then there is a proof of this sort of convergence to solutions of this in Juan's paper, again, under very strong conditions, I think, right? So, but this is the interesting bit for me, right? So this set of STEs now is a potential candidate to try to solve the problem I was describing, right? That's what I'm doing. And then what Juan did, of course, now there are two problems here. First of all, so this new T, so there are STEs. Now we are running sort of instead of, so this is a departure from what EULA idea for MMLE, right? Because EULA was like you run an MCMC chain, you collect your samples, you plug them into the expectation, and then you run a gradient descent algorithm. This is sort of a joint diffusion, right? So now I'm going to discretize. I'm not actually running X first, plugging it into theta. I'm actually taking like a sort of a joint approach, and I'm going to now discretize. One is going to now discretize this joint diffusion, and then this is going to be an algorithm that is you don't have to wait for X and then update theta. Yes. Exactly. So what he does here, yeah, exactly. So you take the problem to space. Right. So what he's going to do exactly is that. So in order to implement this, first, of course, you have two problems. So now discretization, time discretization is one problem, but also you need to approximate this integral is the second problem. And you're exactly what you do for this is one propose this sort of ST, right? So what you have now is that you're running n copies of this diffusion, and then your gradient here is instead of an integral, it's an empirical distribution given by this sort of particles, and you do gradient descent on this, right? The gradient flow in this sort of particle system. Right? Okay, so this is what he proposed. And of course, discretizing this, he proposed a simple sort of discretization. So when you discretize this algorithm, now we have this ST, so for switching, we have this ST. Now, when you discretize this ST, so you have the same step size here, which is, again, I think empirically is not a great idea, but theoretically, this is the sort of algorithm you get. This is the EM with this sort of gradient flow approach algorithm, right? I think he called it particle gradient descent. Basically, you can call it that. Yes.
Would it actually be important to have a batch of this, or have collecting particles, get a mean-rounds, or does a single sample also?
So single sample, in terms of analysis, I will provide this and gives you a convergence rate as well, 1/square of n-type convergence rate. So losing that would be sort of a theoretically worse. But I think the algorithm runs fine with the single sample. But I think in the strongly convex case, everything sort of works. I guess in the non-convex case, that may make a difference. Maybe I can come back to this question. So the differences between SOL, as like Juan argues at least, is SOL is the previous algorithm I described. Instead of now sequential MCMC, you can do this parallelized MCMC step. He actually has some results in sort of because he can parallelize now this IID propagation. As the number of MCMC samples grows, this algorithm obviously is faster. Whether it really helps is a different question, I guess. And then he had this empirical observation where for the posteriors, the approximation tends to have like more mass and details for some reason, right? These are not really explained, I think, but these are empirical differences between so. Okay, it's a different out overall.
And again, you should use, at least in the first equation, you should use the step size, right?
Reduced. That's the other thing. Juan actually didn't provide an analysis for this. I mean, you're saying this for theoretical reasons, I guess. In practice, yeah. So, well, we are going to try to do that, but not with the decreasing step sizes. So we will have this is what I showed the Euler result. We will also have a similar bias at the end. We didn't try really the decreasing step sizes because the algorithm really doesn't work with us. Like it's really hard to make it work. So we try to avoid the yeah.
Yeah, sometimes you would decrease the step size to the first or increase the step size to the, or like just let the second run really, really fast. Then you would come back to the old phase in some sense with the right? Of just getting posterior samples and then doing more grading.
Yeah, I guess if you run it faster, yeah.
Yeah, if you want,
It's a different way. Yeah, we also talked about putting a temperature. I guess that's what you mean.
yeah, making it like a fast slow.
Yeah,
system
yeah.
that one is-
I remember we talked with the great ones about this as well.
For the continuous time problem, so the limit as n goes to infinity, you obtain the Kaplan system of the question located in next because it's like an infinity. This is the idea.
Yes, yes. I mean, this is the intuition from here to here. Actually, what I will do is to forget about this. I will just start from here because these connections are different sort of in field analysis.
And then in the strictly convex case, you have uniform propagation of pairs, so one trajectory should be sufficient.
Yeah, probably, yes. But then the analysis will show is actually there's some nice connection where the non-convexity then can be actually plugged into this.
I mean, it is sufficient, but then you have to slow it down. If you stay in this picture, then you make it really converge, because otherwise you always have noise.
You mean numerically?
No, not numerically. Analytically, right? In the theta, you always have noise in the gradient, so the theta would never converge to anything.
So what you could do to get rid of the noise is rescaling the time in the STE part and letting the correlation length become very small. Yeah, well, and it's kind of learning rate. I mean, that's what we've done.
Yeah, because otherwise it's not.
Yeah, it's just SGD otherwise. It's not correction measure probably not the point.
It would, yeah, but it's a measure, yeah.
It's gonna fluctuate, yes. If you don't.
And the function U, is it symmetric? And it's part
Sorry, which one?
the function U is a symmetric function of K and X.
This one?
Yeah.
No, we don't.
And you don't have any kind of evolution outside.
No. Well, so again, this is what one did was to it was sort of an empirical work. So there was not a lot of assumptions, but there was a joint assumption of strong convexity at some point, but no symmetry as far as I remember. I'll describe what I assume in a bit, because now I'm going to work on this. Okay, there was this slide. Whoever has seen it before, I apologize, right? So like this. So what we did is we came together sort of. How we started working on this algorithm, right? We came together in this sort of Alan Turing Institute. We organized this thing with Sotiris, right? This was a sort of a workshop on accelerating generative models and non-convex optimization, right? Just to advertise. So this was sort of an activity where people supposed to come together and then do work on research problems for whatever, like week or 2 weeks. We had 2 weeks separately. And so this was not a workshop, you just give talks, sort of. So we were trying to identify a problem to solve basically, and we looked at Juan's paper that was just recently it was then just recently out, and then said, okay, this STE looks nice, right? The STE I showed you. There was not a lot of quantitative results about it, the convergence of the STE. So we tried to work on that STE, but then that was the worst thing that could happen in a workshop is that somebody sort of had a COVID, someone tested COVID positive, and then most participants just sort of disappeared. But then what happened is that the sort of Tim and Francesca, we stayed in the room. We so luckily didn't get sick as well. And then we started working on this ST, right? So what happened, what we realized is we looked at this ST. So we start from here. Okay, so that's why I actually sort of ignored or tried to not answer the questions about gradient flows and all that, because we actually forgot about all that. So we said, okay, we look at this ST, so see what happens with this in terms of, so remember also the goal, right? So the goal was to maximize that function that I gave you, the marginal likelihood, the log of the marginal likelihood. So we wanted to see whether this theta dimension will actually converge theta star in some sense, which theta star will be unique in this case because we are under the strong convexity. So in most variables, we are strongly convex. Obviously, these are assumptions to relax, right? For future work. We wanted to see, okay, does this converge? Can we say anything about the theta dimension of this ST or discretization, of course, that whether it converges theta star or not, right? So we looked at this, and then it was kind of hard because our first reaction was to try to identify a stationary measure. Why? Because remember, I showed you the inverse temperature result where if beta goes to infinity, then I can identify that the algorithm will go to maximizer or sample around the maximizer. So what we were trying to see is that can we say that there is a stationary measure that's going to be picked on theta star somehow, in some sense. And of course, because of this ODE, you can imagine that it was not easy to come up with actually an STE that is sort of a stationary measure or identify a stationary measure. Probably, if it exists at all, the theta dimension must be degenerate here, right? So we couldn't solve this problem, but we actually added noise. So we said, okay, we are going to lose something because we don't want noisy theta dimension because we're optimizing in theta somehow. So it's going to result in some fluctuations around theta star eventually, but we can quantify. As long as we can quantify that, maybe it's good enough or not, right? So we come up with this sort of joint ST, and then you can see that the noise is carefully scaled. I don't know if the orange is visible, but you have, it's not just square root of 2, you have square root of 2 over n, right? Okay, so now we started from here. So we have this joint ST, and we are going to try to understand what happens with this sort of system. So there are challenges. First challenge is you figure out the stationary measure. We will then relate it to the theta star, right? You figure the convergence rate of the ST to the stationary measure. So that's sort of a convergence or contraction. So you find the contraction rate and then it leads to convergence. And then, of course, then after discretization, right, this is going to result in some sort of theta n algorithm, like iterates of the algorithm. We want to prove something like this, an upper bound on something like this. Under the setting where u is strongly convex in theta and x, hence that implies that log of p theta y is also strongly convex in theta, and then this is the maximizer, right? Okay, so can we do this for the challenge? All right, so what we have now, I don't know if it's very visible, but I changed notation a bit from now on, which bold, I have now this ST in bold notation. So bold means the continuous time process. It's the same thing, it's written in a bold notation. So this is the ST we're interested in. This is the discretization. This is the Euler discretization of this with the fixed step size. Again, we don't have this run MCMC, get your samples, and then do the gradient descent kind of structure anymore. We have just the joint things are running sort of in parallel, right? And then the hope or the sort of the goal is to say something about the convergence of the theta iterate to the maximalism, right? Okay. What are the assumptions? Now we kept talking about assumptions. These are the assumptions. So we have strong convexity condition on the potential U in both variables. Lipschitz conditions here. So it's Lipschitz, uniformly Lipschitz or globally Lipschitz in both variables. These are, of course, a strong assumption. But this is the first sort of analysis of this sort of system. I think these are going to be relaxed sort of in follow-up work, right? Then also we assume that things are strongly convex, where sort of one way to write strong convexity is like this. We have mu that is a strong convexity constant of U in both variables again, right? Again, this is very strong assumption. So very nice direction is actually relaxing these in X, for example, because it's always, I mean, even if you ensure things are convex in theta, in machine learning, especially things are never convex in X. So this sort of relaxation is going to be very valuable, right? There is the roadmap, sort of, I will provide you. I think it should, sort of, the analysis gets difficult, but the roadmap should work, right? Okay, so what we looked at is that, okay, let's identify a stationary measure first, right? So we have this ST now. And this is the first result. So what we identified now, important point here is that the system now has, so you can think about this with one particle as like, it's on theta and x dimension, right? So it's like a dx plus d theta dimensional. But of course, as you add more particles, this thing becomes like a bigger system, right? Now I have n particles, each dx dimensional, and then I have the theta dimension. So it's like a distribution over theta, but also all sorts of like x1 to n, right? So it's a distribution that lives on a very extended space somehow. And this SDE has a stationary measure of this one. So this was the first result. And this is sort of nice because this is going to be very useful to us in the next slide. In the sense that if we can say something about its convergence to theta star or not. The proof is somewhat standard. Obviously, one way to do it is using the Fokker-Planck equation. I think we also assume that U is C2 because we are solving the Fokker-Planck equation, but I think it's possible to relax that assumption I didn't mention. Okay, so what is nice about the stationary measure is you have this invariant measure, right? It's a good one because if you look at this theta marginal, so you integrate out all the sort of x's, and then you have this sort of representation of the theta marginal, right? It is just a power, it becomes this sort of power to the n. And remember, this was actually, I showed you this integral of exponential minus u was log p theta itself, or p theta y itself, right? So we have eventually something like this. So the theta marginal of this distribution is proportional to this. A better way to write it is because I'm trying to minimize this, remember, this is the marginal likelihood, I'm maximizing this, so minus this, I'm minimizing, I call this kappa, you can get this sort of representation of the stationary measure. What is nice now, remember the beta times v story, where if beta goes to infinity, you will converge to maximizers of v. It's the same story here, but then beta is replaced by the number of particles now, and you have kappa, which is exactly the function that you want to maximize or minimize, right? So what it tells you is that if you let n really sort of large and run the system, theta dimension of the system is going to concentrate on the maximum marginal likelihood estimates, right? This is the first sort of observation. Of course, I didn't talk about convergence rates and so on yet, but this is the stationary measure. What's going to happen to it, basically?
Sorry,
Yeah.
I'm slightly confused. So there's two n, right? The number of particles,
Yes.
and also there's I don't know, the number of axes.
Yes, they are the same. Yeah.
But were there two? Are they two things where they're the same thing?
No, they are the same thing. The number of what do you mean? Number of x's are the number of particles. Yes.
Yes.
So yes, each x is so of course now I'm trying to find a distribution over all those dimensions. So I see this as like n times the x dimensional plus the theta dimensional system. Yes, it's the same thing. You know, distribution over x's and the x's are part.
Yeah.
Okay, so this is a nice result. The first of this encouraging observation is that now, as n large, we are going to actually concentrate more on the margins of theta, right? So as n goes to infinity, theta will concentrate on maximizers of margin. So okay, and then we didn't stop there. We actually tried to prove, so this sort of result is not very meaningful in convex optimization. It's something like if you have a convex function, instead of using optimizer, gradient descent is going to optimize the convex function, but you use a Langevin diffusion, right? And then what happens then? Sort of this is sort of what happens, right? If you, of course, in this case, we have also n because we are targeting that measure that I was showing. We have sort of a non-asymptotic bound around the Dirac around theta stuff or the convex, right? This is trivial, but this is sort of important because this sort of results can be proved in the non-convex case as well. Now, I'm not going to do U non-convex in theta or whatever, but if one wanted to do that, then you would go to our proof, and instead of this, you would use the result for the non-convex case, which is nice. Right? Anyway, so here the sort of point here is that the concentration around the concentration of this margin, theta marginal of this density, which is theta marginal, around the theta star can be quantified like this, right? So this is strong convexity constant, dimension of theta, and then the number of particles, right? It's a non-asymptotic bound somehow.
So you could probably get exactly the same result when you set n to 1 and then scale time in the first equation, right? More in the second.
I'm not
You
sure.
use the scale separation between the two equations. You probably get exactly the same thing, right?
With the noise in the first dimension. With the noise, yes, but then there would not be n. So you mean like you put beta instead of n?
Well, I mean, yeah,
No,
so
I'm not sure.
here you increase n, but it could be the same, I guess. Changing the steps up, I mean,
Or putting beta at the end.
I mean, whatever, the gamma, no, that wasn't gamma, but the beta, that's it.
Putting inverse temperature to the first equation. You mean?
Yeah.
Yeah, I mean, that's what I was wondering, but I think, I don't know if it's possible. I have to check.
But I mean, you get the scale separation because of the square root over n, right?
Yes.
You have kind of, it's like having rescaled the test equation.
Yeah, but here you have to let n go to infinity, I was wondering, I mean, probably do the same, n equal to 1, and then,
Yes, I think,
use the beta.
yeah, so.
It scales basically back to n, but you run in one pocket.
Yeah, that's the slow fast sort of. So if
Yeah,
you do
exactly.
the beta here and beta there,
And you get
it's like
Trade aquaticity, I mean, like
Yes.
sample averages courses.
yes, slow fast. Yeah, I was wondering about this actually. So this,
So actually, where actually showed that, and then so basically an example of where you say, hey, you also have this dynamical system, it's just without the noise in the theta dimension, so it's only for the E and theta. And then you kind of need to rescale time in the SDE by saying, okay, either you kind of let like uniformly the step size get small, whatever that in this case just means that yeah, you make like larger jumps to some extent, or you do it over time and works like that. Yeah, you don't get the conversions rate, we don't get conversions rate, but I can tell you later more about it.
yeah, that would be nice.
Yeah, but
The answers I'm not sure.
we do that. You can just rescale time with a single particle.
Exactly.
And just
Be
rescale time.
dual to each other, right?
It should be pretty much the same thing.
We also do something similar in this paper with under certain urban bias, right? Where we rescale. Because we compute get into plots.
Mhm.
But it's like
Yeah,
say it's also
it's just the same, I mean, it's
Like the average.
related, that's.
Yeah. Okay, yeah, this is the first row. Let's go on. Okay, this is sort of the picture Tinder, so one of the causes is the intuition is roughly like this. So we have 4 particles, and then as you increase your particles, your theta marginal, this is the theta marginal, let's say, and these are the x marginal. As you increase the particles, you basically get a more concentrated distribution around theta. So this was sort of the picture. Okay, so the second challenge is the convergence rate to the stationary measure, right? So we identified this thing as sort of a potentially good thing. We know that it concentrates around the maximizer. We know that sort of the distance of this guy to the theta Dirac on theta star. So how fast we converge? So this is why I showed the Euler result earlier, because this is sort of in similar spirit, right? This is again a Washer time to distance of the iterates of the diffusion. So it's iterates, it's wrong to call that an iterate, it is not discrete time. It's the diffusion, the law of the diffusion at time t, the theta marginal, right? So I'm just looking at the theta marginal. I'm not interested in the other stuff because those are tools for me. I'm estimating the gradient somehow with x's. Okay, the law of this diffusion to its stationary measure. It's exactly very sort of similar to Euler, which is very nice, right? We did this in terms of, if you want technical sort of details, it's actually a nice way to analyze this. Instead of analyzing theta and x's themselves, actually it results in sort of a, not a great bound. If you rescale your system like this and analyze everything in terms of z, and then keep the theta dimension, so get theta results from there, it actually like results in a very nice sort of bound. Okay, so we managed to do this. So it's sort of very similar to Euler. You have the Z0, Z star. Okay, it's important to distinguish now to theta star, which was unfortunately not distinguished in the first preprint of the paper. Theta star here is the maximizer of U theta x theta dimension, because it's different than actually when I integrate things out, you have log p theta, the theta star of log p theta is going to be different, right? Because there's 2 theta stars. Anyway, this is sort of the first one. And it's driven by exactly like Euler, so you have an exponentially fast convergence under this strong convexity condition. This is the initial condition, error comes from the initial condition. And this is the interesting bit. Now you can see that actually if you sort of take this term out, dx is controlled by mu, right? So you can, how strongly convex you are is actually mitigating the error induced by x dimensions. And theta, you have sort of a d theta over n term. And whether actually this term is optimal or should be there is a question. I think this term is mainly there because we injected theta noise, right? So we actually are not doing something so optimal in the setting. So this is the sort of the price we pay to see that. Okay. Exponential convergence result, like EULA, but sort of an extended case. Okay, so the final result, I don't know, I actually have no idea. Well, 10 more minutes, I think it's going to be enough. I'm going to briefly mention the sort of the final bit of the analysis, where if you want to analyze sort of a discrete algorithm, right? This was the discrete algorithm we wanted to analyze at the end of the day. What you do in sort of what we did, at least in this setting, is that you identify a continuous time system, right? That is going to agree with the discrete time system on discrete time. So if for any n, this system is defined so that this gamma n, this distribution, okay, this has to be t somehow here. The distribution of this theta gamma bar n is going to be same as theta n. So what this does, what this is giving us is that now then, instead of analyzing, because once you discretize it, of course, there's a discretization error, and exactly this is how you prove discretization error in some sense, is that you construct a continuous time system that agrees with the discrete time system, but then you can actually compute the distance between this and the original continuous time system, right? I'm not going to go into too much detail here. It's a bit of a messy computer. It's the most difficult part already in the analysis, and thankfully we had a team doing all the time. Okay. This is the result of the discretization error, right? So now this is the diffusion of the continuous time, n is missing here. This is the diffusion in the continuous time, theta marginal of that. And this is the iterate of the algorithm. Again, n is missing here. So this is the discretized version. And the error is controlled like this. You have a square root of gamma sort of discretization error, right? Standard sort of rate again. And again, you can see the terms are similar. We have one d theta over n term and one dx term. And this C is sort of not explicit, but is independent of every explicit in paper somewhere in the appendix, but it's independent of everything you would care, right? So there is no hidden dependence to anything there. All right, so why did we all do all this? Finally, to conclude. So remember, the goal was to bound something like this. So we wanted this algorithm theta dimension to converge to theta star, and then we wanted actually to bound this. And because theta star now this kind of relationship holds because this Dirac is a sort of a deterministic distribution or deterministic measure, right? And because of this representation, we can actually write our sort of things we want to bound in this form. And then the rest is basically using the fact that W2 is a metric, and then do this sort of splitting, right? This is the final bit. So the final bit is this thing I proved as the concentration, right? The stationary measure. And then this thing was the convergence, exponential convergence to the stationary measure. And this is the last bit showed just before in the slide, this discretization error, right? So basically all the bounds I showed you, I just add them together, and that gives me an upper bound of this, basically. Yeah.
You're assuming only one minimum, right?
Yes, because of the strong convexity. Yes. Yeah, exactly. Yes, both variables. But then if you integrate, there's this Prekopalinder inequality, so you can show that it's also the integral also will be. So what I was going to say, yes, this is important though, because this result can be replaced by sort of a non-convex. So there are in the literature, if you assume the potential dissipatives is hard to long to describe, you can actually have sort of non-asymptotic bounds again here for the non-convex cases, right? Which is sort of the proof technique would go through, but everything would change one by one. You have to prove then converges under a setting with the potential dissipative, and then the discretization actually gets much worse. You have to prove fourth moments are bounded, things like that. It's very messy, but can be done. Yeah, this is the final result, right? So what I did is I added everything together, and this is what we get, sort of a convergence rate. So the discussion, of course, now, which is curious for me, is that whether injecting noise in theta dimension, right, is actually necessary, because the first term comes from that, which we wouldn't have if we had a way to manage like without injecting noise and analyzing the ODE, because we are in the strongly convex case, that ODE should converge without actually noise in it. So that's one question. Of course, then the question is whether these theta terms are actually going to disappear as well. Whether if you can use the theta dimension without noise, right? But this is the final result. Okay, So the nice thing about this result is it's fully explicit in terms of dimension. You know the step size dependence somehow, right? You don't need to necessarily decrease with a very certain schedule, your step size. There is no funny dependence of things to each other. Somehow, like you need to, assume things are exactly right for the bound to hold. This is sort of a generic bound, except of course there are step size restrictions and so on, but these are kind of standard. And as I keep saying, it's possible to extend, although not easy necessarily, to non-convex sort of cases. Although you ask me a lot of questions, probably I don't know if you could answer all of them, but in theory or in sort of principle, it should be possible to extend this because Langevin diffusions have non-convex optimization guarantees, right? And they are non-asymptotic as well in this paper. We wrote with again Sotiris and with Ying. And also, like, an easy sort of target is that you can obviously then change the analysis here with sort of you plug and play other things, right? You can change the Langevin diffusion optimizes sort of a realistic conditions for, so instead of having both Lipschitz and both strongly convex, you can relax conditions and so on. And of course, then because of the setting, generality of the setting that I was mentioning, you can apply to a large number of problems where you can have a bound or you can have a guarantee in your sort of application, right? I think that's all. The papers, if you want, this is the paper of Valentin, and this, sort of a nice paper using unadjusted Langevin algorithm. Juan's paper, which is also very nice, that we took the SD from, right? And then this is our paper, and this is the paper where you can find sort of a non-asymptotic guarantees for SGLB, which is the reason I'm telling you that it's possible to do for non-convex optimization as well. That's it. Yeah.
Maybe it's a dumb question, but you said that if you try to get to the minimizers by setting the temperature really high,
Yes.
once,
Yes.
it's really high.
Yes.
Do you observe the same thing by setting n, which plays also the same role?
Very large.
Very
Yes.
high. It's
Yes.
maybe done by.
No. So we didn't. I mean, in this paper, so our paper was meant to be an analysis somehow of this paper, which had no noise in the theta dimension. They did experiments like very high dimensional settings with low number of particles. So maybe it is the case. I think because in their case, they haven't really tried. I don't know what you have in mind, maybe 10,000 particles, 1 million particles.
Okay, but
I think nobody
there's
tried.
Annealing, like
Changing the
increasing
number.
it and,
Yes, maybe not. I don't know. The problem with annealing is that the theorems sort of are going to be tricky to adapt to. But I think what one did in this paper is that they tried for really tricky problems with high dimensional problems. Things seem to work, but it's always low number of particles, which is good news. But obviously, then the optimization result is a bit weak in that setting. Yeah.
makes sense.
Thank you.